Okay, so you guys are pretty comfortable and pretty confident with the horizontally launched projectiles. Of course, very often we don't just kick them straight off a surface, we kick them up. We angle their launches. So this gets us horizontally launched projectiles. And we will actually start off with a really stupid but kind of, well, it's stupid but fun little thing on Joe Genius. It's on YouTube, and we'll pull that here. Okay, so when we launch something at an angle, the only thing that's really changed is we still have a constant x velocity, but now we have a y component to the initial. So the x, again, x velocity is constant. I can't say that enough. Y velocity changes, and that's all about gravity. So that whole skill you've built of breaking apart the vectors, now you're going to end up using on the initial velocity. Suddenly the initial velocity is not just initial velocity. So if we have a football being kicked, if we have an angle with the horizontal of, we'll say 23.0 degrees, and we have an initial velocity of, I don't know, 38.0 meters per second. Can you find, of course you can, the VIY, whoops, and VIX? Of course you can. It's just trig. This is the same thing that you've done before. Well, now when we list variables, when we start with the x and y variables, we're going to have, very often we don't have either the angle or the initial velocity. So what we'll start to do is list the expressions that we create for VIX and VIY. So in this case, of course, VIX is opposite, so VI sine theta equals VIX. Because VIY is adjacent, VI cosine theta equals VIY. And we'll actually just put those right into our table of variables. It's remarkably simple, but these problems do get complex. In the horizontally launched projectiles, remember how something canceled out every time? That's no longer true, because we now have that VIY. So we'll actually do one together. We'll do the sample problem. And then if you want to pick away at the book ones, that's what, 4 or 5 problems. And I will publish, I've got videos already made with hints and tips for each of those that I'll link to Classroom, so that over break, if you want to work on those, you have a way to get unstuck if you're stuck. So this is the sample problem for 3E, and this is the angled launch projectile, and it sounds completely insane. The zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, the zookeeper kneels 10 meters from the light pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. The monkey tricky little monkey tries to trick the zookeeper by dropping a banana at the moment that just before she fires her dart. And if the tranquilizer dart travels at 50 meters per second, will it hit the monkey, the banana, or neither? That arm is terrible. I'll give it a nice bright yellow banana. Okay, so we're going to mark out our problem. Really this is just a ballistics problem, but here's the actual thing that is kind of cool, kind of fascinating. As this bullet travels, and that's not a good representation. At every single moment in its flight path, there is a y component to the velocity and an x component, a y component and an x component, a y component and an x component. Now, the x component isn't changing ever. It's constant. The y component, of course, is shrinking until at the very top of flight, there's no y component. There's still an x component. That x component is constant. So our job is, again, we use time to connect the axes because time gives us a way to define the moment at which this is true and this is true. So we're going to first of all just try to talk about what we can figure out here. So first of all, we have the light pole 10 meters away. So we've got 10.0 meters is the delta x we're interested in. Is that actually the delta x of the bullet? Is that where it comes to ground? Well, we don't know. But what we're interested in is when delta x equals 10 meters, what else is true? Because what we don't know is where on the y-axis that thing is at the point when delta x is 10 meters. So that's our big question. If we go ahead and list our variables, x-axis, y-axis, Vix equals, and we can do our little triangle here. We've got our angle, or we don't have our angle yet, but we will. Vi cosine theta. Did I screw that up on the last slide? Viy is adjacent, so that's going to be Vi. Oh my gosh. I'm screwing everything up, and you people aren't even yelling at me. X is opposite, it's sine theta. Viy is Vi cosine theta. We obviously have no acceleration on the x. We do have acceleration on the y equal to negative g, or negative 9.81 meters per second squared. We have a delta x of 10 meters. That's the point we're interested in. We want to know, really, where on the y-axis this thing exists, delta y, and I'm going to put in a subscript notation here. I often do this. Delta y when delta x equals 10 meters. Because, I mean, we can look at overall delta y, we can look at delta y at some point on the x-axis. You know, that's all negotiable. As was the case with the horizontally launched projectiles, time provides the bridge between the two axes. So, I've used that same equation that ties displacement, initial velocity, time, and acceleration together for both axes. Now, I said, unlike horizontally launched projectiles, we don't have something cancel on each of them, but we still have something that cancels on the x-axis because there's no acceleration. So that goes away, and we are left with delta x equals Vix delta t, which means that delta x over Vix equals delta t. Now, it's really, really important here that you put that expression in now, because if you put in your entire value for Vi, all hope is lost. You know, do not meddle in the affairs of dragons, for thou art crunchy and good with ketchup. Is that it? So delta x over, well, this is Vi sine theta equals delta t. Over here, nothing cancels. But we do have this little beauty that we can plug in two locations. And we end up with an expression that's already rearranged for delta y, which is pretty handy. So delta y equals Viy times delta x over Vi sine theta plus 1/2 a sub y times delta x over vi sine theta quantity squared. Well, we have to do the same thing for this that we did for the VIX. So delta y equals VI cosine theta. And I'm going to go ahead and distribute that across the parentheses. Delta x over VI sine theta plus 1/2 a sub y times delta x squared over VI squared sine squared theta. And the way you note that VI squared sine squared theta is really important because the VI is squared and the sine is squared. Theta is not squared. So at this point, do you see anything that can cancel? I do. VI goes away. What's nice about that is if you need to use this equation to solve for an initial velocity, as long as you've got everything else, you've got initial velocity over here, and it cancels out in the first part of the equation. So let's rewrite that. Delta y equals cosine theta delta x over sine theta plus 1, well, I'm going to distribute the 1/2 and the ay as well. Ay delta x squared over 2 vi squared sine squared theta. You know the trig identity, cosine divided by sine equals tangent. And we can walk through the geometry of proving that, but that also simplifies the math here. You can leave it cosine over sine, but it's uglier down the road. Are we ready to plug in numbers? There's one key piece that we're missing. That's okay. Didn't know if you were expressing pain at the physics or something else. We don't have the angle. That's a problem. Well, we don't. And what they give us in this problem is the fact that the tip of the gun is 1 meter off the ground and the light post is 5 meters off the ground. So we have a difference of 4 meters. So we have 4 meters, 10 meters, and they expect that you can find the angle. So we'll actually wrap it up. I mean, to quote a physics prof I had in college, you see where this is going, right? You can actually finish this calculation on your own at this point. The book does it actually slightly differently on this sample problem, but I think this is actually a cleaner way to do it and more straightforward. So what this gives us is where on the y-axis what the change in y position is from the muzzle of the gun to where the bullet is, the tranquilizer dart, when it's 10 meters from the gun. And, I mean, spoiler alert, it's a sample problem. It's all in the book. She hits the banana. Clever little monkey. Apparently the monkey goes on to fight another day, and the banana goes to sleep. But the problems in the book are assigned. They're not easy. If you're hiding out in here tomorrow and you want to pick away at them, you're welcome to do so. I'll actually have the worksheets ready tomorrow with the answers. I can have them today if you want. And over break, I will post all of the hints and tips on the 3E problems so that if you want to do a little bit of work over break, you can. That's it.